now I see my slides. Thank you very much for being here. 1 second. Okay. All right. So today we are going to talk about pKa predictions for large and drug-like molecules which contain complications. And the complications are conformational and tautomeric effects. So since we are going to talk about something complicated today, I thought that it would be a good idea to start with something simple. And something simple can be, for example, the basics of pKa and pKa prediction. So let's look at some of the simple and basic concepts. Here is a simple molecule. This is the drug aspirin. It contains a single carboxylic group. It is the only group here that can possibly dissociate or accept a proton in a reasonable pH range. And the process of the deprotonation of this molecule is very simple. So the pKa for this process is written as a negative logarithm of 2 parts. The first part in the numerator is the unprotonated concentration or concentration of the unprotonated form, the concentration of free protons in the solution divided by the concentration of the protonated form. So the pKa of this molecule is 369. So that's how pKa is defined. That's a simple molecule, nothing to worry about here. There's a simple unprotonated form and a single protonated form in this equation. So that's it. Now, what is pKa and why it is important in drug discovery? pKa affects many molecular and physiological characteristics of a potential drug. For example, it can affect its solubility because ionized forms are likely to be more soluble in water. It can affect ADME properties. It affects lipophilicity. The protonation state depends on pKa. You want to know what protonation state binds to your target, and this protonation state depends on the pKa of the drug. Finally, you have blood-brain barrier penetration. So if you are designing a drug, pKa is certainly a good property to know because you want to cover all of these properties and effects. So this is why people in drug discovery are interested in pKa prediction. So the molecule I showed before on the previous slide was simple. It contained a single functional group. It contained only one form on the left-hand side of the equation and one form on the right-hand side of the equation. But the drugs that we deal with normally in drug discovery and in real world are usually more complicated than aspirin. So there are some examples of these drugs which are more complicated that I'm showing here in this slide. For example, we have this drug, the dasatinib, which contains multiple protonation sites, and it contains a lot of conformational flexibility. There is this poison. It's not a drug, but it's a drug-like molecule. It's a poison. It's a mushroom poison called arelanine. It's a fascinating molecule because it contains a complicated tautomerism here. You have a lot of different ways to distribute protons in this molecule in the protonated and deprotonated forms. So you also have conformational flexibility, and you also have intramolecular hydrogen bonds, which are hard to describe with some solvation models that we are using in pKa prediction. There is a drug, sildenafil, which contains a heterocycle in its core, which is prone to tautomerism. And of course, there are lots of rotational or prone to rotation bonds, and this promises conformational flexibility. Finally, there is cocaine that contains an intramolecular hydrogen bond, which creates a stereocenter, and it creates special complications, and I will mention this later in the presentation. Okay, these were the complicated molecules, some examples that I showed. And of course, to to describe pKa, there are multiple ways of doing that. In a review from 2011, there were multiple pKa prediction methods listed. There were at least 43 empirical pKa prediction methods listed, again, as of 2011, and then 23 quantum chemical methods as of 2011. Now, of course, there are probably 100 methods, if not more, that can predict pKa, and new methods are constantly being published. What is the difference between empirical and quantum chemical pKa prediction methods? Empirical methods rely heavily on experimental pKa data and QSR-like approaches. They are fast, but the empirical approach doesn't produce much physical insight. You just get a number, and you don't know why the pKa of something is 6 or 5, even though it's accurate. It just matches the experiment well, but you don't know the answer why. It is usually good for well-known functional groups, but when your molecules become more complicated, contain more unusual functional groups and more functional groups in number, you probably want to use a quantum chemical method because it relies heavily on quantum calculations, so basically ab initio calculations from the first principles. It may use some pKa data for parameterization, or it can be parameter-free. The drawback of quantum chemical methods for pKa predictions is that they are slow. It produces much more physical insight than empirical methods, though. So you have an explanation of why certain, you can kind of decompose the answer because you can see the intermediate results, can see the intermediate energetics of the conformations and of the tautomers, and you can understand what effects, what structural parameters contribute to the pKa of this drug that you are studying. It might be better for unusual structures, as I mentioned. It covers all kinds of groups usually, including rare functional groups, transition metals, etc. And it's good for 3D effects, such as spherical clashes, hydrogen bonds, etc. Okay, so now I said there were about, my estimation is that there are about 100 different pKa prediction methods, at least published in the literature. So given the abundance of these methods, do we need any more pKa prediction methods? And the answer to this is yes, because the methods that are listed or were mentioned in the previous couple of slides were basically designed for coverage or description of simple drugs, maybe something like aspirin. But currently, in my opinion, there are no good, reliable methods that describe molecules like this with conformational complications, with tautomeric complications. So yes, we do. We need more methods, and we need more methods geared toward realistic molecules like these. One such method, so I said there were no such method, but we believe we are developing one such method. It is developed in the program called Jaguar pKa. And it's designed, and Jaguar pKa is designed for to treat realistic drug-like molecules from first principles. Here are some basic details about Jaguar pKa, and I will give you more information in the next few slides. So Jaguar pKa, of course, uses quantum calculations, and the quantum and 3D effects in Jaguar pKa are covered via the density functional theory, DFT. Conformational effects are covered with the molecular mechanics program macro model through force fields. We also describe solvation effects via the Poisson-Boltzmann equation and its numerical solution. We are doing, of course, implicit solvation calculations because explicit solvation calculations are very expensive. Tautomeric effects, something that we'll be talking about in the second part of this talk, are described with the program called macro pKa, which can be viewed as an extension of Jaguar pKa. It's a program we are currently developing. It uses a lot of machinery from Jaguar pKa, but it goes one step further. I will show you in a few slides. what it does. Macro pKa seamlessly generates tautomers, conformers, computes micro pKas, and outputs macro pKa. Now, I have mentioned the words micro and macro pKas. What do they mean? This is very important for understanding the complexity of proton equilibria in water solutions. We need to understand the difference between micro pKas and macro pKas. Okay, so the next few slides are going to show or explain this difference. So let's start with a pKa titration curve. So for example, we start with low pH and we add a strong base such as sodium OH to the solution, and we see a pKa transition here. Then as we add more base to the solution, we maybe get another pKa transition. So these transitions are called macro pKas. This is something we see in the experiment, typically in titration, and these are just transition between charged forms. So for example, this can be a transition between charge 0 and -1, macro pKa 1, and macro pKa 2 is the next transition between charge -1 and -2. Charge 0 forms are it's actually not necessarily a single form. It can be all of these microspecies. It can be tautomers and conformers of charge 0. So they exist here, for example, at pH 1. But as we add the base to the solution, these forms become other forms, and they transform to charge -1 because a proton is stripped from them, and they just become different forms of charge -1. And finally, there may be another set of forms of charge -2, and so on. So notice that we can actually compute a pKa between two individual microspecies, two individual tautomers, for example. And these pKa, which we normally compute in quantum chemical calculations, is called micro pKa. There can be, of course, multiple micro pKas. We can concoct a micro pKa between two individual species, and we can get a number from theoretical calculations. So that's good, but in the experiment we see macro pKas. So can we do something to compute macro pKas that is available from the experiment from micro pKas that are available from the calculations? Yes, we can. So we normally compute micro pKas in quantum chemical calculations, such as in Jaguar pKa calculations, and then we assemble those micro pKas into the final macro pKa. I'm going to show you how micro pKa predictions work. Actually, this slide, I have shown it so many times already. This is basically an overview of how micro pKa prediction works. I'm not going to talk about all the details of micro pKa predictions because this presentation is about macro pKa predictions, about how you assemble these micro pKas into macro pKa, but I'm going to show you something about micro pKa anyway. In micro pKa calculations, you need to basically define your process, your protonation or deprotonation process. In the GUI, in Maestro, that's the graphical interface that hosts the Jaguar pKa program. You indicate the pKa atom, which defines the micro pKa process. Which atom is going to be protonated? For example, this is going to be this nitrogen. And then what we do, we generate the protonated form and the deprotonated form from this structure separately. We do conformational search on those two forms. We do quantum chemical calculations shown here. And finally, we assemble the pKa from the thermodynamic cycle because we can compute all these energies quantum chemically in solution and gas phase, assemble everything and compute the pKa. The pKa is actually called the raw pKa because it's an unrefined pKa. It's still the basic number that we get from the theoretical calculations. And in order to get something close to the experiment, we actually need to correct it by empirical parameters. Why the empirical parameters? That's needed for higher accuracy. If we are aiming at covering a large chunk of chemical space, all the functional groups, then we absolutely need to use those parameters, because even small errors here in quantum chemical calculations and the description of solvated species can lead to potentially large errors in pKa. So we need these parameters for higher accuracy. And what's actually good about these parameters is that observations show that for specific functional groups, for let's say one functional group, let's say amines or phenols, the errors that we are making in this thermodynamic cycle are systematic. So for different functional groups, we can develop different parameters. And there is a set of functional groups that are currently available in Jaguar pKa, which are covered. So if your compound is one of or belongs to one of these functional groups, or your compound has one of the functional groups that are represented here, then we have high quality parameters for these functional groups. But what if it doesn't? Then we approximate the parameters on the fly. Basically, as you're doing the calculations, we construct these parameters for your functional group by doing some clever mathematics. We are learning from the structure of your molecule and from the available basis set of these parameters for these functional groups, and basically interpolating these parameters to represent your molecule in the best possible way, even if we don't have specific parameters for your functional group. So this usually works very well. And now I'm going to talk about actual pKa predictions for more complicated molecules. And we're going to start with this drug, the dasatinib, which contains multiple protonation sites. What we normally do for such molecules, notice that it has all these nitrogens there. What we normally do, we start with a maximally deprotonated structure. And that would be represented with charge -1 here. And notice that there are 3 structures here that I was able to draw. I draw them by hand in this sort of manual approach. You need to draw or create all these molecules that you think are reasonable at charge -1. And that corresponds to starting with a very, let's say, high pH. You can do the same thing with maximally protonating your molecule and start with a very low pH. This is as you wish. And then you need to do a thorough conformational search for every micro pKa you're going to calculate. So in the GUI, in Maestro, again, this is the graphical interface for Jaguar pKa. We have these options to perform a thorough conformational search. This is very important to do conformational search. And you will be doing this to calculate micro pKa for each of these transitions from charge -1 to charge 0. Notice that for charge 0, here we have a single tautomer, single molecule. And you calculate a micro pKa for every transition from every tautomer with charge -1 to this single tautomer of charge 0. If you had multiple tautomers of charge 0, you would have to calculate all the combinations of these micro pKas. Then you can combine these micro pKas into the final macro pKas using this formula. This formula is very well known, was published multiple times. You can find more information about it in this paper shown below. And this formula is composed of micro pKas. These are the numbers we just calculated, and you can compute macro pKa from it. You repeat this process until you get all the macro pKas in this calculation. So that's what we did here, and we computed macro pKa, of 9.9, 7.3, and 3.6 for 3 pKa transitions. This agreed pretty well with the experimental numbers shown in the orange color. Notice that for macro pKa 3.6, we combined 3 micro pKas, 2.5, 3.5, and 2.9, using that formula that I showed before. The macro pKa 3.6 is composed, you can think of it this way, of these 3 numbers, and the number 3.5 makes the largest contribution. It is swayed a little bit to become 3.6 by 2.9 and 2.5. So you see, actually, if your micro pKas differ by, let's say, more than 1 pKa unit, then the influence of those pKas that differ by 1 pKa unit on the dominant pKa will be fairly small, so you can neglect them. In this case, the macro pKa shifted a little bit. There are some cases, though, where the macro pKa can be fairly well influenced by the micro pKas, for example, when 2 different tautomers have very similar pKas. But this case was basically simple. You draw all these molecules by hand, you do these micro pKa calculations, and you get these macro pKas. I said simple, conceptually simple, but in practice this is very complicated because for every molecule that you need to calculate pKas of, you need to do kind of this network of micro pKas and then combine the macro pKas by hand, essentially. This is not good. I will be talking a little later in this talk about the more convenient way of doing this, using the macro pKa program. But currently, for using Jaguar pKa, this is what you would be doing for molecules like the dasatinib. When I mentioned that we needed to compute conformations using a thorough conformational search, I was serious about this, because if you don't do conformational search, for example, if you start with 2 different conformations and don't do conformational search, your results will depend on the conformation you start from. For example, in this test set, we had a bunch of molecules, and we had conformation A, conformation B of molecules with various substituents. These conformations A and B differ by a flip, trans, and cis. And then if we do a mean unsigned error, even the mean unsigned error, I'm not even talking about the individual pK predictions, even the mean unsigned error is already different. You see there's a huge difference depending on what conformation you start from, even though it's the same molecule. It's not good. If you do conformational search, here's a fast conformational search available in Jaguar pKa, then your pKas become much more similar. If you look at the individual pKas, they're kind of close, and this is reflected by the average. But if you do a thorough conformational search, even when you take one conformation of the thorough conformational search, you get you get a very close to convergence already. And if you take up to 10 conformations, I think this is already at the level of noise where the results cannot get any better than this. So this is why you want to do a thorough conformational search. Notice that it is more important to do a thorough conformational search and take one conformation for quantum calculations in the end than to maybe do a fast conformational search and take, let's say, 5 conformations for quantum chemical calculations. Does the number of conformations for quantum chemical calculations matter? It matters a little bit. So look at these results. They were published in the paper shown below. So we have very large and complicated molecules here, and these are their mean unsigned errors and the number of outliers. And you can see that depending on the number of conformations you take and how you do conformational search, no conformational search, regular conformational search, and then there is an aggressive conformational search with 1 conformation, 5 conformations, and 10 conformations. You get progressively fewer outliers. and lower mean unsigned errors. So the number of conformations that you take for final quantum calculations matters, but not much. I think a good balance between the accuracy and computational expense is 5 conformations. That's what I normally do use in my calculations, but if I want the best possible results ever I usually run my calculations with 10 conformations and, of course, aggressive conformational search. Here are some other results that demonstrate the difference. Well, they demonstrate the accuracy of the Jaguar pKa method, but they also demonstrate the difference between empirical methods and non-empirical methods, quantum chemical methods and empirical methods for a group of these molecules. So in these molecules, stereochemistry actually matters. It affects the final pKa, and the differences in stereochemistry here are important. These things are actually diastereomers. They're not non-enantiomers. So the dipole moments of these molecules are different, and subsequently the pKa's can be different. And if you look at molecules, for example, 1 and 2, their pKa's are fairly different. 771 and 941 are large differences. So if we look at the experimental pKa's for these molecules and the different DFT-based methods available in Jaguar pKa, and also comparison with 2 empirical programs, Chemicalize and EPIC, you will see that the quantum chemical programs follow the experimental trend, but the empirical programs are actually insensitive to the stereochemistry itself and don't follow the experimental trend. But if you compute the mean unsigned error, all these methods predict pretty good results. So the trends here are reproduced by DFT-based methods, but not by empirical methods. We have seen such results in many cases, and that's just one little example. Okay, now we're going to talk about this complicated molecule cocaine, which contains an intramolecular hydrogen bond, which stabilizes the protonated form. So notice what happens here. This is actually interesting. So if you start with the protonated form and it's in the wrong stereochemistry because this protonation creates a stereocenter, then what's going to happen is that when you sample conformations using, let's say, a force field program like macro model, then the program doesn't want to change the stereo center, stereo conformation, or stereo configuration of this molecule. So it's not going to create the alternative form. So if you start with that one, the bad one that is not stabilized by the hydrogen bond, then no matter what sampling you do, because you normally don't let your molecular mechanics program to invert stereo configurations, then no matter what sampling you do, you will not find this hydrogen bond. So this is a weird example, but here you need to be careful. And the best thing to do here is start with the protonation form that has this hydrogen bond, which stabilizes the molecule. So if we start with the right protonation form, then the pKa is very close to the experiment, 9.4 versus 8.8. But if we start with the bad protonation form, again, the stereo center here is not going to be inverted when the molecular mechanics program samples the conformations, and the hydrogen bond is not going to be found, and the final pKa is going to be bad, 5.9. Well, of course, in the solution, this proton pops off and on, and this conformation or stereo configuration always inverts, but not in the calculation. So be careful with molecules like this. Okay, I've been talking about conformational complications so far, about intermolecular hydrogen bonds, about sampling those conformations, and I was showing the importance of doing conformational search, thorough conformational search, and maybe mention some other conformational stuff. But now we want to talk about tautomers. This is an even more difficult topic. Here are some details, or maybe some points about the program we are developing at Schrödinger called MacroPKa. We are building a completely automated MacroPKa predictor for organic molecules. So the idea behind it is that you pass this kind of molecule to the program that that is prone to tautomerism, and the program does everything for you automatically. It automatically generates these tautomers. It basically figures out which kinds of which hydrogens can jump among different proton acceptors, like these nitrogens or oxygens or sulfur. It accounts for conformational effects in the manner that I showed in the previous few slides. So we do utilize all of this knowledge that we learned about doing conformational search in the GIGO pKa program, and we use it in MacroPKa program. We automatically compute entropic and symmetry factors in case there is symmetry in the molecule. So we only need to compute a protonation channel once, and then we account for the symmetry automatically. We do perform large or coverage of chemical space, so we cover all kinds of functional groups. Our approach works on all kinds of heterocycles, all kinds of functional groups, not just, let's say, amines or thiols or alcohols. We decided, well, since the coverage is large, but chemical space is infinite, and there are things like transition metals and like surfaces, so we decided to focus on drug-like molecules to begin with, and we wanted to predict MacroPKa in any pH range. We postulated that the results should not depend on initially chosen conformation, tautomer, or resonance structure, or Lewis structure. So you can draw your molecule in any way, but the program will automatically sample everything and make sure that the results don't depend on the initial structure. Then we parameterize microPKAs on thousands of experimental data. We do DFT calculations for everything. All the final energies are computed by DFT. DFT is very, very important. If you don't do DFT, if you decide to cut corners, if you decide to do some kind of lookup data, this is good, but without DFT energies, we found that the results cannot be so good for a large area of chemical space. And then we thought that accuracy was more important than speed. So currently we are doing a sort of a brute force approach, computing all possible tautomers and conformers and assembling all the data just to get more accurate results. The program is still in development, and we are doing, of course, improvements to the efficiency of it. And I'm going to show you some results now and some observations about predicting MacroPKAs of molecules as complicated as these. Why are these molecules complicated? Because here is an example of a molecule that actually exists only in one, maybe, or two tautomers in solution that are sufficiently highly populated. But this molecule contains multiple tautomers in charge 0, charge -1, and charge -2. For example, here we have 70 tautomers. Actually, only 1 or 2 of them contribute to the molecule as it exists in solution. But you don't know which one a priori, and the distribution of these tautomers depends on the substituents in this molecule. So you really need to calculate all of these forms sort of by hand and assemble all the results. So this calculation would be pretty much intractable if you did it by hand. The macro-pKa theory is simple. So we have these protonated tautomers on the left-hand side and deprotonated tautomers on the right-hand side. And if we define the micro constant like this for every pair of deprotonated and protonated tautomers, then, as I said, we can assemble this macro-pKa or macro-Ka. If you want pKa, take a negative logarithm of it, and you're done. You need to just generate all these tautomers and also assemble the results into the final result. So the tautomer populations can be computed like this, and you can actually calculate macro-pKa using these tautomer populations using a single micro-pKa. These two formulas are exactly the same, equivalent, but notice that you still need to calculate these tautomer populations. Any formula you wish to use, it's up to you, same result. Okay, how does macro-pKa work? Macro-pKa, of course, is assembled from micro-pKas, and the micro-pKas are computed from DFT calculations. They require tautomer generation, and they require implicit salvation model calculations. So for the implicit salvation model, we are using PBF, which is the Poisson-Boltzmann finite elements model. It's a numerical solution of the Poisson-Boltzmann equation. It contains empirical corrections for first shell effects, basically hydrogen interactions with the solvent, with water, which is not covered with an implicit salvation model. It does not depend on Lewis structures. We have improved the model so that the results only depend on XYZ coordinates. Some results of macro-pKas, macro-pKa predictions. As I said, we are still improving this program, but it is fully functional, and I think it works great already. And there are some results that I wanted to share with you to show some of the interesting things we have learned about macro-pKas and about tautomeric effects, especially about how we can now calculate all of this automatically. So do tautomers matter? Here is an example where the tautomers actually don't matter that much. Look at this molecule. It looks fairly complicated. We thought that the original tautomer of it was this one shown on the left. So if we modeled this tautomer by hand, the pKa that Jaguar pKa would predict for it would be 7.94. But when we plug this molecule into macro-pKa, macro-pKa said that this was not a dominant tautomer, according to our salvation model, of course. It said that this tautomer represented only 30% of the whole population of all the forms, which are 0. And the dominant tautomer was actually this one, 61%. And notice that even if we started with a tautomer that we hypothesized that is actually not the dominant one, the pKa of it would be 7.94. And if we took that pKa, it would still be very close to the experiment, 8.02. So here we would be just lucky. But it turns out the right pKa prediction is actually 8.44, even though it's slightly worse, slightly farther away from the experiment. If we take into account all these three tautomers and their micro-pKas, that's the final macro-pKa that we would get. So in this case, the tautomer, even though it is not the most populated, would still predict us would still give us a good pKa prediction. Here is a case where it actually would give us a pretty bad pKa prediction. In this case, we at first thought that the initial tautomer was the one shown on the left here. This is the triazole molecule, and we thought that this tautomer, just because of human intuition, we thought it was the dominant one. Macro pKa said that it was not the dominant one. Macro pKa said that this tautomer is only, well, occupies only 4% of all the species in solution. And if we use that tautomer, then the resultant pKa would be 4.96, which is far from the experimental result, 6.4. It turns out that the dominant tautomer here is this one on the right, 70%. And if we combine all the micro pKas into a single macro pKa, we would get the answer 6.33, which is much closer to the experiment. So the lesson here is that sometimes these tautomers don't matter really because you just get lucky, like here, but sometimes they do matter. And the safest thing to do is just do macro pKa and make sure that you are considering all the tautomers and that you are treating all the tautomers sort of in a democratic way, and then selecting those that contribute, well, not selecting, you actually summing everything up, but effectively you will choose, or you will describe all the tautomers, and the tautomer that is dominant will be automatically taken into account. All right. Of course, macro pKa calculations have been done before, and these papers in the early 2000s by Bill Goddard group from Caltech represent some important initial steps in macro pKa calculations. And there was a series of papers written by Bill Goddard's group. In some papers, there was only one molecule essentially examined. For example, guanine in this 2003 paper was studied in detail. All the conformations, all the tautomers were studied, all the energetics, all the effects, and then all the micro pKas were computed and assembled into the final macro pKa. So there was a whole paper by several people dedicated to computing macro pKa of this molecule and investigating its tautomeric effects. There were some other papers like these, and the one shown at the top, we were studying uracils, and the one in the middle, or they were studying these four molecules. So I thought that since now we have Jaguar pKa and macro pKa, especially macro pKa, I can just plug in these molecules and essentially reproduce these results, or should be able to, in a matter of, I don't know, just whatever it takes for these calculations to finish. I don't do any manual selection of these tautomers, any conformational selections. I just plug in these molecules. I don't do any atom selections, and I just run these calculations and obtain my results. So here are some results. But maybe before we look at the results, let me mention one important thing about these papers, is that in the papers by Goddard, as far as I understand, I read them and I see that what they did, they essentially chose the parameters of the salvation model that better represented the experimental pKa. In our calculations, we didn't do any manual selection of parameters that better reproduced the experiment. We just took the black box method macro pKa, we generated all the tautomers and all of the conformers, and then assembled all the energies into the final macro pKas. And here are the results. The Goddard results are a little better than ours, but the correlation of Goddard and co-workers and our correlation are actually very good. Our correlation is 0.92, and the mean unsigned error is 0.76. This is not perfect, but I believe that this is still fairly respected, should be fairly respected result, because it's below 1 for molecules as complicated as this, prone to tautomerism, considering the number of underlying calculations that are done here. This is impressive. 0.76 is a good result. Also, don't forget that I mentioned that, of course, those manual papers or papers in which pKa was calculated manually, of course, they chose the parameters so that the results agree with the experiment. There are several comments on this in the paper. There's another paper, again, where the parameters were chosen so that the final pKa's are or agree better with the experiment. And in macro pKa, we don't do any manual selection of parameters or basis sets. Everything is completely automated, and it just becomes a black box method. So in this case, we again get a worse agreement with experiment than Goddard. Again, below 1 pKa unit, this is a still pretty good result. But notice that there are some very low and very high pHs here. And in the experiment, even the experimentalists couldn't measure these pKa's exactly. So they said it's just less than 0 or about 0.8. And these pKa at large pH, I also, well, from what I understand, these pKa's are hard to measure at very high pH and at very low pH. They are uncertain. So if we remove them just to see if we can do better in a pH range, which is more important for drug discovery. So if you remove those data, uncertain data at large and low pH, we actually are doing now a little better than Goddard and co-workers, and our correlation is just equally good, and we get as good a result as it can get. So I would estimate that or conclude that macro pKa does an excellent job here figuring out all the tautomers, conformers, launching all the calculations in a black box manner, and finally printing the macro pKa result, and of course all the populations of all the tautomers. We did multiple such calculations, so I'm showing just some glimpses and such results. Of course, we are running macro pKa calculations on all kinds of things, and here is just a slice of some of those results. Macro pKa test on structures prone to tautomerism. There are 38 structures in this test set. Notice that these structures are fairly nasty. They contain all these mobile hydrogens that can jump around these nitrogens, oxygens, sulfurs, and the dominant tautomer is not always certain here. So these structures are complicated and would be very hard to treat with the regular Jaguar pKa approach. On these structures, we got 0.62 mean unsigned error in pKa units, and I believe this is a good result. So let me conclude this talk by saying that, let us return to the first part of the talk. Remember, we were talking about first simple molecules and then molecules that contain conformational complications. Simple, non-flexible molecules like aspirin, of course, don't require an extensive conformational search, and frankly, they should be well treated by even empirical methods. But a thorough conformational sampling and search is absolutely necessary for accurate pKa predictions. So a thorough conformational search is more important than considering several conformations. So we believe that if you take 1 or even 5 conformations, this is sufficient. So you don't need to take 20 or 50 conformations for final pKa predictions. But the more conformations you take, up to 10, the more stable your results become, the fewer outliers you're going to get. So this was about the conclusions about conformations, and conclusions about tautomers are that we have developed and are still actually developing and improving a seamless and completely automated macro pKa prediction workflow or method based on DFT calculations. The program is called macro pKa. The workflow sets up tautomers, conformers, all for you. It computes micro pKa's for you and outputs a single macro pKa. And of course, you can also output tautomer distributions as part of kind of byproduct of the workflow. At present, so you remember I showed that molecule where I showed a manual approach to do pKa predictions for micro pKa's and then assembling them into macro pKa's. Currently, macro pKa works for molecules as large as that, but when you have too many protonation sites and mobile protons, you will just get too many tautomers. And for complicated molecules like that with lots of protonation sites, we currently recommend doing Jaguar pKa sort of manually still, although we are working on filtering the gigantic number of these tautomers that don't really contribute to anything in the end, and we're working on this. But if you want to use macro pKa, it is best to just kind of truncate your molecule and work on the heterocycle core. But of course, we are developing a solution that treats large molecules even with lots of protonation sites and mobile protons completely automatically, basically developing a single solution for treating conformational and tautomeric complications in one single program that I think will be called just macro pKa. So with that, I would like to thank you for your attention and welcome.